3 teachers with different backgrounds have come to CLEEPS, the school science support service, to find out about teaching radioactivity.
I haven't taught radioactivity before. I'd be quite nervous in teaching radioactivity because of the dangers of it and because of my lack of experience and knowledge in teaching it.
I've been a physics teacher for, well, this will be my 5th year. I've taught radioactivity at GCSE in all those years, as well as teaching it at A-level.
I'm currently a PGCE student and I've just started my 2nd placement, and so I've got no experience of teaching radioactivity yet.
Radioactivity is something that people are naturally quite nervous about. They think it's dangerous, or they feel it might be damaging themselves, or they've got themselves in risk. However, when done carefully and safely, these experiments are completely fine.
Schools have been using radioactive substances in their laboratories for many years now, probably 30, 40 years, and they're extremely safe, very, very low activity, and provided they're looked after properly and used properly, there really aren't any problems.
I can open up the container using forceps and making sure that I'm holding them at least 10 centimetres away. I carefully take the lead lid off the container, lift it out, stand it on the lead lid. I use the radioactive source, ensuring I'm not pointing at myself or the pupils.
How far back should the students stand?
Well, as we can see, you're about 1.5 metres away, and the same should be true when you're doing this with your pupils. Ensure there's a good distance between where you're demonstrating it and where the students are standing. When I've finished, I replace it back into the lead container, put the lead lid back on again, and ensure the source is back inside.
The most important thing is that the radioactives are kept secure, also that they're kept in a steel container, so that in the event of a fire, the radioactive material would be contained safely within that.
If you'd like more information on handling radioactive sources, speak to your head of science or contact CLEEPS.
I always think it's important to start a topic with something to grab the attention of the children. And if your pupils are seeing something that they're engaged in and something which is a little bit novel, a little bit unusual, then you've got them. Now you're being silly, aren't you? I'm going to send you all off, and you're going to find a place to hang your balloon, and then when you get there, you're going to charge the balloon by rubbing it with the cloth, and we'll go back and collect it. Release the air out slowly as you let it down onto the paper. Here I've got a balloon that has not been inflated and has not been around the lab. I'm going to test it with the Geiger counter to see if I can get a count from it. As you can see, there is no count. Jill, would you like to pass yours across? And if we test it with the Geiger counter, we can notice that there's a significantly higher count.
That's quite a difference.
It is, and that's not really what you would expect from just hanging it in the corner of the lab.
So it's become radioactive over an hour then?
Oh, let's be careful. Has the balloon become radioactive?
It's just attracted the dust particles.
Good. Something stuck to it.
Yeah, so by charging it, what we've done is we've had the dust particles stick to it, and those have got the decay products of the radon gas that is found naturally in the air.
I think the balloon experiment really stands out because it's interactive.
Some everyday objects will register on a Geiger counter. The results may surprise the students. First is a domestic smoke detector.
And there's a slight count, and the reason for that is that inside the smoke detector is an americium source which produces alpha and a small amount of gamma. The alphas are stopped by the smoke if it's inside the chamber, which will then trigger the alarm to sound. So yes, it's radioactive, but not very.
That's quite surprising because you wouldn't expect a household product to be made with a radioactive source in it.
You could also try an old watch with a luminous dial.
Wow.
Whoa.
So, a very significant count there.
Now, the worrying thing is I'm sure I had one of those when I was a kid.
Although ionising radiation is coming out of the clock face, the radium-based paint is safely sealed inside. There's no contamination outside. There's no radioactive material where we don't want it.
In this demonstration, we're going to show the properties of ionising radiation. And to do that, I'm going to use a gold leaf electroscope. If it's not charged, the leaf hangs vertically downwards. To charge it, I'm going to use electrostatics, and I'm going to rub a piece of Perspex rod and then transfer that to the electroscope.
We can also charge the electroscope by using an EHT power supply set to 2000 volts.
I'm going to show that the ionising radiation from the radioactive source will cause the electroscope to discharge. Then I'm going to show the pupils that the forceps on their own have no effect on the electroscope, but when I put the radioactive source in, you can see that the leaf starts to fall down because the ionising radiation is allowing the plate to discharge.
This experiment shows how ionising radiation can allow a current to flow between two parallel plates.
The one on the left here is attached to the positive side of an EHT power supply, and the negative plate is connected through an electroscope back to the negative terminal of the supply.
Where would you get those plates from?
These plates are actually the tops of electroscopes, which I've connected into 4mm plugs, connected into a piece of dowling. It also has the bonus that this acts as an insulator from the high voltages from the power supply.
In this experiment, we're using a 5,000 volt extra high tension power supply, which some teachers worry quite a bit about. But in fact, if you're using one that's been supplied for school science use, it will be current limited to less than 5 milliamps, which means that electric shocks from it are harmless.
Now if I mount the radioactive source and aim it between the plates, the electroscope leaf starts to rise, showing that there's ionisation happening between the plates, allowing the charge to move for the electricity to flow around the circuit.
Why not use an ammeter?
You could use an ammeter. The trouble is that the amount of charge that's moving is very small. So measuring that as a current, you'd need a picoammeter. So we use the electroscope instead because most schools will have an electroscope and you can use that in the circuit. I've got my radioactive source at the bottom, allowing the ionising radiation to come between the plates. Each of those sparkles is representing an air particle which is being ionised. As we zoom in, the animation will show us each individual air particles and the ionising radiation coming from the bottom. It'll rip an electron from the surface, which is attracted towards the positive plate, and the ionised air particle is then attracted towards the negative plate and drifts sideways. This is happening all through the air particles, and what you can see is the ionised air will drift one way and the electrons are accelerated the other way, allowing the current to flow. If we zoom back out again, then we will see that this causes the electric current to flow between the two, which is what we've seen on the meter from the demonstration.
The cloud chamber uses dry ice, which you can either buy or make yourself using a carbon dioxide cylinder.
The carbon dioxide cylinder you have to make sure you've got is called a siphoning cylinder. You can recognise it because it will say liquid withdrawal on the sticker and also have a white painted line down the side of the cylinder. To make the dry ice, we have to attach the dry ice attachment to the valve, like so. The nozzle has to face downwards and the nut is tightened but not over-tightened.
Dry ice can cause severe burns to the hands, so it's important to wear thick fabric gloves when handling them, for example, the sort that you can get from garden centres.
So if you'd like to put your safety specs on as well. When I open the cylinder, the liquid carbon dioxide will come into the chamber here. And as the dry ice is formed inside, you'll hear it starting to block the tube, close the valve, and our dry ice is ready to collect. And you'll see inside the solid carbon dioxide into a plastic tray.
I hadn't even considered that I could make my own solid CO2 for use. I think I'll be going back and trying to see if we can acquire the apparatus for that.
We're now going to have a look at the cloud chamber. The first job is to put the alcohol around the edge.
Why use alcohol?
Alcohol is a dipole molecule, meaning that it'll be attracted towards the ionised air particle. When I find the source for the cloud chamber, you'll see it's mounted in a cork in a metal tin. I'm going to pick the source up by the cork, and I'm not going to touch the end which is covered with the luminous paint which contains radium. I carefully thread it through, and the cork also seals the chamber and stops the alcohol vapour from coming out. So now it's time to put the dry ice into the bottom of the chamber. I'm not going to pack it to the top, I'm just going to put enough in to cover the bottom of the chamber, and then put the sponge in to hold it in place, and attach the bottom and turn it to lock it in place. Once you've done that, you can turn the chamber back over. We can use the small wedges to ensure that it's flat on the table. And we're now ready to illuminate the chamber. You can then view from the top of the chamber to see the tracks produced by the ionising radiation.
The cloud chamber was my personal favourite. I thought it was really quite amazing to be able to see the activity of a single alpha particle and be able to visualise it. And I think the students would really enjoy that.
So here I've got the tracks from the radioactive source, leaving their trails as they streak through the saturated vapour. But on the small scale, let's follow one of those particles as it ionises the air on its way through. In slow motion, let's have a look and watch the alpha particle getting close to one of the air particles, ripping an electron from the outer shells, and you'll see them scattering away either way. So it gets close, it strips the electron and carries on moving. So as soon as the particle is ionised, the alcohol starts to be drawn towards it, clumping together and starting to form the track that we've seen in the cloud chamber. If we zoom out slightly from that, you'll see this is happening around every single particle that's been ionised, and that will leave a trail of the alcohol.
We've seen that radiation can ionise the air and the tracks that this can form. Next, we're looking at counting the individual alpha particles.
I'm going to connect the negative side of the high voltage power supply to the grill on the top of the spark counter. Underneath the grill, you'll see there's a thin wire which I'm going to connect to the positive side of the power supply.
Teachers sometimes find spark counters don't work very well. The main cause of problems seems to be dust. We recommend the spark counters are kept in plastic bags to avoid build-up of dust.
As I increase the voltage, in the end I will get a spark between the mesh at the top and the wire underneath. If I reduce the voltage down from that though, I want the point where it's just stopped sparking. When I introduce the radioactive source, which is producing alpha particles, when one of those alpha particles fires through the gap between the mesh and the wire, it causes a spark. That's because each alpha particle, as it passes through, is causing ionisation, allowing a spark to happen between the grill and the wire. We can see the mesh across the top, which is connected to the negative side of the power supply, and the wire underneath, which is connected to the high voltage positive side. As the ionising radiation comes in, it causes the sparks to happen. As we zoom in, an alpha particle is coming from above, and it ionises one of the air particles between the gap. That's then accelerated upwards, and that causes a cascade of ions hitting each other, which we see as a spark. Each ionisation particle coming in is going to cause a spark of its own.
spark counter can also be used to look at the absorption properties of alpha radiation using an americium source.
I'm going to hold the source so the alphas are being detected. When I put the paper in the way, it stops. To show that paper stops the alpha particles from getting through. I can now point out the range of the alpha particles, which is a few centimetres in air.
A more controlled way of handling the radioactive source is to mount it in a dowel rod and clamp it in a retort stand.
I think the idea of using dowels as holders and clamp stands is excellent. It actually allows you a lot more flexibility. And I'm going to go back and get my technicians to prepare me a set of dowels, because I think that's what I want to do from now on.
In this experiment, we'll be using a Geiger-Müller tube to measure beta and gamma radiation.
The tube has got a protective cover on the front, which if I carefully remove, you can see a very thin window which allows the radiation to pass in. This one here has had the end of the tube removed, revealing a central wire which is positively charged and a cylinder which is the negative connection. Every time the radiation comes in, it'll trigger an event which can then be counted by a machine.
Schools may have different types of meters, but essentially they all provide the same function: to provide the voltage to the Geiger-Müller tube and count the events.
Whenever you're setting up a radioactive source, you always make sure it isn't pointing at people. And a good setup is to use a retort stand with the radioactive source pointing downwards all the time and the Geiger-Müller tube at the bottom. Whenever you're using a Geiger-Müller tube, particularly if you're holding it in a clamp, it's very important to make sure you don't squeeze it too hard, because that too could damage the window.
For this experiment, use a pure beta source such as strontium-90.
I can get an audible representation of how much radiation I'm measuring. The first thing to do is to show that, unlike the alpha particles which are stopped by paper, the beta particles aren't. So putting a piece of paper in makes no difference at all. However, if I bring a piece of aluminium in, we can hear that the beta particles are completely stopped, because the range of beta particles is a few millimetres of aluminium.
What happens to the beta radiation?
As the beta particle enters the aluminium, it'll slow down, losing energy. In the end, it's likely to become part of the sea of electrons. The other thing we can demonstrate is the range of the beta particles in air, and if I move the source away from the detector, you'll hear that the count rate decreases. And notice that the range in air is significantly larger than the alpha particles, which was 2 or 3 centimetres. We're at tens of centimetres and still getting a reading on the counter. This time I'm going to use cobalt-60 as my gamma source. So I'm going to mount the gamma source above the Geiger-Müller tube.
That's quite a lot lower count rate.
There's two answers to that. The first is that the Geiger-Müller tube is not as good at detecting gamma rays. And secondly, the number of gamma rays produced by this source is quite low. If I put the aluminium in the way, the aluminium is not absorbing many of the gamma rays as they pass through. However, if I introduce some lead, it's only with a couple of centimetres of lead in the way that the count rate is significantly reduced, because gamma rays can pass through lead, but several centimetres starts to significantly reduce the number getting through.
Reduced but not stopped.
Yeah, to completely stop the count rate, we have to have several tens of centimetres of lead.
Why is it that lead stops it as opposed to another metal like aluminium?
OK, the aluminium itself is quite a light metal. Its density isn't very high, as opposed to lead, which is very dense, which will absorb the gamma rays as they pass through.
Handling the absorbers with the bare hands is quite safe. The problem arises if you're tempted to put the absorber close to the source with your fingers. So we always recommend that an absorber should be handled with forceps if you've got a radioactive source nearby.
What you see here are the three types of radiation streaming towards you. On the right-hand side here are the gamma photons. In the middle is the helium nucleus, the alpha particle, 2 protons, 2 neutrons. And on the left-hand side is the beta particle, the very fast electron. You'll notice that the gamma rays and the beta particles are almost travelling at the same speed. That's because the beta particle is travelling at a speed quite close to the speed of light. If I bring a piece of paper in, what you'll notice is the alpha particles are now unable to penetrate through. The gamma rays and the beta particles, though, can still get through. If I bring a piece of aluminium in, that's enough to absorb the beta particles, and they are no longer getting through, and there's no significant reduction in the number of gamma rays. If I bring in a large piece of lead, that is enough to absorb a significant number of the gamma rays, and the count rate drops right down.
Using the absorption demonstrations is a really useful way to check students' understanding of the penetrating properties of radiation.
The other thing that we can start to try and show with this setup is how the range of the gamma rays in air is linked to the inverse square law. So hopefully if I double the distance they are away, the count rate will go down by a factor of 4. So at the moment my source is roughly 4 centimetres away, and if I double that to 8 centimetres, the source will now be counting at about a quarter the count rate.
After having watched the alpha, beta and gamma absorption practicals, I think that I would be able to perform that in the classroom, along with the animation, which would help the kids' understanding.
This experiment shows that beta particles are negatively charged.
I've got them at an angle to each other so that the detector is not collecting the radiation as it's fired from the source. The aluminium plate is to block any stray beta particles from going straight into the Geiger-Müller tube. I can then use a magnetic field to deflect those beta particles around the shield into the detector. So as I bring the magnetic field in, the count rate increases significantly as they're deflected into the detector. And just to confirm that it's not the metal plate, if I reverse the field and bring it back in, I can see the count rate doesn't change because they're not being deflected towards the counter. I can confirm this with Fleming's left-hand rule, with my first finger representing the field, my second finger pointing in the opposite direction to the beta particles, and my thumb showing the direction that they will be deflected into the detector.
Once the students have seen some of the properties of alpha, beta and gamma radiation, you can start to discuss what they are. This is a good starter activity that will allow you to visualise it.
What you've got there is the hat is going to represent the centre of the atom, the nucleus, and the balls attached to the outside are going to represent the electrons around the outside. And what I'm going to do is I'm going to sort of simulate the idea of the ionising radiation as being fired towards you. Now, I'm going to start with the light polystyrene ball. I'm going to try and knock off the electron hit. Or I could try the golf ball, and I'm not going to do that yet. But
you could ask students to discuss how these model the different types of ionising radiation.
A pulse of smoke.
I thought they were really good starters. They would be really great for rousing enthusiasm.
Using the protactinium generator, we can measure the half-life of a radioactive isotope. Once it is shaken, the decay can be measured using a Geiger-Müller tube.
What I need to do is to record the count rate every 10 seconds over 5 or 6 minutes. Reset the timer, and I'm going to write down the count rate every 10 seconds. And 10 seconds, 154. I've reset the counter, and what will happen is over the 5 or 6 minutes, that count rate for 10 seconds will decrease as the half-life of the radioactive isotope continues on its decay curve.
Another way to measure the decay rate is with a computer data logger, which will plot the results on a graph. The count rate will increase for the first few seconds, so we exclude those. You can highlight that the points don't make a smooth curve because of the random nature of decay. But drawing a smooth curve through the points shows the trend of the readings. To help demonstrate decay and its random nature, you could get your students to play games like these. Flicking coins randomly eliminates players and is fairly quick.
If you're ahead, you stay in the game.
I'm out.
So Julie and I...
Tails!
I'm tails too, so we both lose.
And you can demonstrate isotopes with a longer half-life with dice, which have a lower probability of decay.
If you get a 6, then you're out of the game. You've got a 6, so Julie is out.
Another way is to use cubes with one side painted white. Mix them up and pick out all the cubes with the white upwards. Repeating this a number of times, the students can count each result and plot a decay curve.
It's really good in demonstrating the random nature of radioactive decay, isn't it?
Yes.
I've learnt there's an awful lot you can actually do. There's a big range of experiments you can do.
With a bit of practice now, I feel confident enough that I will be able to perform the practicals and demonstrations safely.
Actually, I'm teaching radioactivity next week, so I'm really looking forward to doing so.